Welcome to the second episode of the RockyTerrain Podcast. We've actually done it. It's unbelievable.
Yeah, we're back, and I hope with more interesting facts to discuss.
Yeah. My name is Thomas, and with me is, as always, Dennis.
Yeah.
And yeah, it's kind of unbelievable that we actually in the second episode, this podcast is now planned for us both for such a long time. And I don't know, I'm really feeling hyped about this.
Yeah, I mean, we're almost at episode 100 at this point. We've done it all, we've discussed it all, and what's left to do?
Yeah, we already recorded like 100 podcasts beforehand.
Yeah, at least we tried 100 times.
Yeah, no, but it's our second episode, and with the second episode, we want to go in like the more of a standard routine for our podcast.
Indeed.
And therefore, I guess it would be nice to just talk about a little bit more about our personal lives. Dennis,
once again,
this is something new in your life.
Yeah, actually, different things, different news from my side. I have started working on a different project, dealing with a pathology in 3 neck vertebrae of a cattle, potentially a bison. It's 3 isolated vertebrae, and therefore it's pretty difficult. It can be pretty challenging to figure out whether it's bos or bison, which of both genera. And yeah, otherwise, the new semester has started. So
yeah, I had my first courses or classes this day and
yesterday. Yeah, exactly. Me too.
I saw these vertebrae you're writing on. You showed me them like some months ago. Or a year ago, actually.
Yeah, back when I discovered them in the collection.
Yeah. They were creepy.
Yeah, you're going to see what we're going to publish on this. It's a pretty
interesting.
It's pretty crazy.
Yeah,
yeah, but other things, as I've talked about in the previous episode, I'm into vertebrate paleontology, and my favorite prehistoric animals are pterosaurs. So, winged flying cousins of the dinosaurs. And 2 papers have been published this past week, which were pretty interesting, because one was from Bestwick et al., published in Nature Communication, which was about dental microwear. So they took teeth from pterosaurs, at least from pterosaurs which had teeth, because not all pterosaurs had teeth. Some lost them. Some only had a bill, like birds. And what they did is they looked at the microstructures on teeth, because depending on what you eat, your meals will leave different kinds of structures, textures on your teeth. And with that, they could determine that different pterosaurs ate different things. We've been thinking that for a while now, that they weren't just restricted to eating fish, as is often depicted. And yeah, this is pretty interesting, because they found a broad array from fish to potentially meat from tetrapods, so land vertebrates, small land vertebrates, to insects and all kinds of stuff. So that's pretty cool, and it confirms that pterosaurs were more diverse than often anticipated.
Correct me here. Didn't some of them lose their teeth and then later evolved again like teeth-like structures?
That actually happened in birds.
Yeah.
So in pterosaurs, I wouldn't know about that.
Okay.
But it happened in birds, with the pelagornithids. These they were in the news last week as well, because they are actually potentially the biggest birds in terms of wingspan to ever take to the skies. They developed pseudo teeth, so basically what they did, they evolved tips on their beak, which look like teeth, but they are just structures from the beak itself, no real teeth. Yeah, so that was the one paper, and the other paper from Venditti et al. Was published in Nature, which also concerned pterosaurs, but this one was about their flight efficiency, which was pretty interesting because this ties in very neatly with the topic of pterosaur diversity, because what they found is, first of all, pterosaurs became more efficient flyers over time. So what they did is they created biophysical models of pterosaurs, and then essentially they tested via, computer-ish methods, mathematics, stuff I don't really know much about, how efficient they could fly. So, meaning how much energy do you have to invest to fly a certain distance. And they became more efficient progressively, but one thing which was pretty interesting is that Ashdarchoids, so maybe the most derived pterosaurs, the most derived pterosaur group, actually didn't really fit into this model, because although they are the most derived and potentially the latest pterosaur group to still exist until they went extinct at the end of the Cretaceous, it seems that they didn't really invest much into flight efficiency. Some taxa seem to be pretty efficient, some seem to be less efficient, but overall they are not really the most efficient flyers. It's interesting because they have been predicted to be more terrestrial than other pterosaurs, because they have pretty long legs, pretty big feet. There are multiple lines of evidence pointing towards them potentially being more terrestrial animals, from trackways, track fossils to their general anatomy. And it wasn't only that, because they also tested their sinking rate. So, how far do they sink when just gliding ahead? How much do they sink per unit of time? And it turns out they tended to sink faster than other derived pterosaurs. They seemed to sink faster, meaning they couldn't glide for as long stretches as other pterosaurs potentially could. So pretty neat, because this just might point towards their more terrestrial habits. I mean, it's just one aspect, but I mean, if a flying animal reduces its flight efficiency and ability to glide far stretches, it's at least a good hint.
That's very interesting. I'm trying to imagine a lifestyle where you kind of live very terrestrial, but can also fly at certain times.
Yeah, I mean, it's basically what Mark Whitten and Darren Naish have proposed, that they're a lot like storks. So, yeah, I mean, terrestrial foraging is the term often used. Because, I mean, storks, especially think of shoe-billed storks, they don't really fly much. They can fly, but they tend to do it less than other birds. And I mean, showbill storks are pretty extreme. Pelicans and storks, they do fly. Generally, maybe not as much as other birds, but they do, and they can. So yeah, that these papers, I thought I would like to mention them because they were pretty interesting to me.
When we talk about storks, there's something I can say here. So I actually, before I went to university, I worked at our little nature reservoir close to my hometown. And this year, because of some reason, they had a lot of storks. Like, never before they had so many storks. So what I've done, they used a crane and built some kind of structure where they, with like 8 possible spots for storks to nest. And actually, all of them were used. And nowadays, are the picture where it's just this one crane structure near a forest. And it's completely full of storks.
Yeah, it's cool. We had, in Barve, which is where we dig at a lower Cretaceous dig site. I wasn't there this year, and we had reports of black storks coming in. They tend to live in Eastern Europe more, but an ornithologist of our museum, he told us that black storks, they tend to come over to Central Europe more and more. Pretty interesting. They're pretty shy animals. I would have loved to see them, but wasn't there, unfortunately. But Thomas, I think we should switch over to you because I've been talking a long time now. What's going on?
Pterosaurs are also interesting.
Yeah, I mean, pterosaurs are brilliant. But, yeah, I guess planets are kind of interesting as well, so... Yeah, come on. What's up with you?
Yeah, so... First of all, university started again, so I'm in the master now. No more bachelor classes.
Yeah.
No, it's my first week in master. Everything, at least that I do this semester is online, at least now for November. But I guess it works fine, so I don't have problems with that since then. All the classes are really interesting. The topics that we talk about are, well, we can choose our classes in master, and everything I choose is kinda part of planetary sciences. So I have geophysics, I have physics and chemistry of the inner Earth, geology of the terrestrial planets, remote sensing. So everything I'm doing is based now on planetary sciences.
Just one question.
And this is pretty cool. I mean, yeah.
Just one question. You've been pretty enthusiastic about remote sensing.
Yeah.
Why is that?
So first of all, this class is with my professor that I really like. Then we're like 4 people in this class. And we're going to talk about, well, remote sensing. So how do satellites work? What can we do with satellites? We start from the basic, like physics. We talk about orbits and all that stuff. And then we go farther into satellite technique, what different techniques there are to study different planets and how these different factors or how these different methods work and how we can actually learn more about different planets with the help of satellites and spacecraft. And I don't know, I just like the introduction. This first, we hadn't even a real class. It was just like, what are we going to do this year? And this was really cool.
Yeah, I just thought it might be interesting because maybe not everybody knows what remote sensing is, because I didn't know. I didn't know what this course was about.
Oh, okay, yeah. Remote sensing is basically just remote, which means, not human. and sensing. So basically just try to study and plan it with a satellite.
Yeah.
Yeah, this was pretty cool. And then also physics and chemistry of the inner Earth sounds also really amazing. We talk about heat fluxes, fluid dynamics, mantle convections, plate tectonics again, and yeah, I'm really looking forward for this semester. Yeah, and then I finished kinda my bachelor thesis.
Kinda.
So, yeah, I'm finished with my text. There are some parts in the discussion we have to work on a little bit more, I guess. I hope that I can do this tomorrow. And then I'm finished. And I have 1 week to go to correct mistakes, to read it again and again and again, and yeah, try to completely finish it. And then I can submit it next week.
And how are you feeling about it?
First of all, I'm really hyped just to have finished it, because when I started, I couldn't see the end product. I couldn't visualize it. And now I just know that's it. I have it here. I can read it. I can go through it. And it was not that easy actually for me, because, this topic I'm working on, and once I have submitted it, I think I'm going to talk about it in the podcast. But it's so important for me, this topic, and it really grew to my heart. And this is something that I want to work on in the future too. And I've put so much work into it. And I'm kind of a perfectionist when it comes to these things. And then it's extremely difficult to say, that's it. I don't know, I have something in my mind. I wrote it, and I just couldn't connect with what I've written. And so I kind of had problems in getting into the process. But it actually, at one point, it just worked. And so I'm really happy about it. I like my figures. I like my discussion. I think there's quite some cool things that I can discuss, and then that I can add like to the discussion at the moment in this field of view. So planetary tectonics. I think there are quite some cool things that I found. So my results are also, I like them.
Yeah, I mean, we are going to, or at least it's the plan to make an own podcast episode about your thesis sometime down the line, my thesis.
Yeah, and then, you did the first correction. So
basically, yeah.
You found like the most mistakes since then. Then I've already some other people read it since then.
Oh, this is what I'm going to outline to everyone. All the minute little mistakes you made.
Yeah, so now it's just you actually found, I think, most of them. The other people don't found that much. So yeah, I'm kind of hyped. I'm really happy with it. But yeah, let's see what the grade is.
Yeah, I think you don't have to worry too much.
Yeah. Weird feeling to have finished it.
Yeah.
Yeah, then, maybe a last topic for this introduction for today. So yesterday evening, because now I have time again, I watched The Theory of Everything, so the movie about Stephen Hawking. It was on my list for a very long time, but I don't know, I never watched it, I don't know why. And then you've watched it like 1 or 2 weeks ago. So you got me inspired to now actually watch it, and it's heavy.
Yeah, it was one of the few movies. I love talking movies. I love dissecting movies into every single last detail, be it in terms of dialogue, plot, anything, choice of music, camera work. But This one, it was tough.
It got me.
Didn't. Yeah, it completely ripped me apart. I don't know.
So first of all, I suspect that it would be like a lot of just about his work.
Yeah. I mean, maybe we should say that it's the movie about Stephen Hawking's life.
Yeah, and it's focused on his personal life. Like the work that he's done it is part of the movie, but like the focus is just on his personal life. And I did not suspect that when I started watching the movie, and this really got me. Wow.
Yeah, that's. I didn't even expect that. I didn't know what to expect going in. And I was pretty surprised that his scientific achievements, basically, they were mentioned. But I like that we got to see Stephen Hawking the person and his personal struggle behind, behind his scientific work.
And I guess what also was a big factor for me watching this movie is that I've told you this before. I'm kind of an hypochondria. I think that's how you say it in English. So, which basically is kind of the fear of illness. And I don't know, since my childhood, there are two illnesses that just, they're stuck with me. Two illnesses that I was really afraid of since I'm a very little child. And these are ALS and Parkinson, which are two very close related illnesses. And ALS is the illness that Stephen Hawking had. And I'm always afraid of these illnesses. Just just imagine losing the control of your body, and to see him, such a person I really admire, and the acting was so believable that wow, I was emotionally torn apart.
It's an extreme situation to act, and I think Eddie Redmayne he nailed it. I was very, very skeptical going in, but honestly, it's I don't even know what to say. It's an incredible film, movie, whatever. Go watch it.
Yeah, you have to watch it, but be prepared. Yeah. Be prepared. Yeah.
Okay.
All right. I guess let this be our introduction for today. Let's do a small pause and then move on to our main topic of today.
So for episode 2 of our RockyTerrain podcast, we decided to discuss a topic which is very close to our hearts. It's a topic which is pretty complicated, which is pretty complex. So let's see how we're gonna do with our time. But Thomas, would you like to explain what we want to talk about?
Yeah, sure. So once again, we're trying to put a topic, well, they would have probably talked about hours and hours to put in 1 to 2 hours. So let's see how that works. So what we want to talk about today is basically the archive of Earth sciences. And this archive is patchy. This archive is unorganized and incomplete. And things are difficult to find. You probably won't find all your answers at one spot, but you have to look at many different ways to kind of be able to find the answer you're looking for. Because we have one problem in geology, or Earth sciences in general, and this is that time itself seems to want to destroy its own evidence. And the farther we go in the past, the more holes and inconsistencies we see, and, well, the more dangerous they are to make mistakes. So, if I can put it in your words, because I really like them, we want to talk about the things that we can know and the things that we cannot know.
Yeah, indeed. It's about trying to fix or trying to interpret a book which is missing a lot of essential pages. But what we're trying to show is that we still can interpret this book. It's possible to draw conclusions despite the missing pages, or despite the fact that some pages are heavily water damaged or, have been painted on by a little child. So, but I mean, why exactly is the rock record patchy? That's the first thing we need to discuss and to get into to understand why exactly we even want to talk about this topic. The rock record is patchy because Earth is a very, very, very dynamic place. Things are going on and changing all the time. And for the first things first, rocks are created all the time because magma rises from Earth's interior, forming new rocks underground, or if this magma reaches the surface, it might also form new rock on Earth's surface.
So we had to learn the number for our system Earth exam 1 or 2 years ago. Do you still know it? How much magmatic rock is produced every year?
No.
Yeah, I had to look also. I forgot it also. It's exactly, if we trust our professor, it's exactly 33.6 cubic kilometers per year if we combine all the different sources of rock formation. And magmatic rock formation, important.
So meaning underground and volcanic.
Yeah, so first of all, like the mid-ocean ridges, where all the time new ocean floor is created, then the volcanic sources, that subduction zones, and volcanoes within the continental crusts. So like all this combined gives us this number.
Yeah. But we have to keep in mind that's only one side of this whole coin, because rocks aren't just created. Once they are exposed to the elements, well, what happens is weathering, which leads to, the breakdown of these rocks. This is how sediment is created. And this sediment then is subject to erosion which leads to the sediment being redeposited somewhere else, where it can then form sedimentary rocks once again. For instance, if enough sediment collects, let's take the example of a beach. At a beach, then it starts to compress the lower layers, the older layers of sediment. And this pressure can then lead to the formation of new rocks.
Yeah, so these are sedimentary rocks. So we already covered the magmatic rocks, or volcanic rocks, which are produced due magmatic and volcanic activity. And then we also have sedimentary rocks, which are produced through sedimentation.
Exactly. And, the one thing we have to keep in mind is that there is a third type of rock involved, and this is metamorphic rock, which is what happens when volcanic or magmatic rocks in general and sedimentary rocks are exposed to extreme pressures and temperatures. Imagine two continents colliding. What happens is that rocks are exposed to excruciating pressures, which then lead to a complete rearrangement, or can lead to a complete rearrangement of these rocks.
Yeah, and with that, we already talked about a lot of different cases where a lot of information is actually lost. I mean, a rock that is like, had a rock that experienced very high temperatures and very high pressures, as you said, changes its own structure and its own chemistry. And with that, we already lose a lot of information about how the rock originally looked like, and a lot of information, geochemical information that we would have gathered if the rock was not deformed later.
Exactly, and we should not forget that rocks can be lost altogether because we have subduction zones on Earth. And what's going on there is that rocks are, well, subducted. They dive back down into the Earth where they are remolten, and after remelting these rocks, nothing is left. They are magma once again, which can in return produce completely new rocks, but this is information lost forever. Information we just cannot know about.
We have some small minerals that we may think were actually recycled but survived, or small parts of them survived that are now, well, very, very small areas in new rocks that we found that could have been, well, these are mostly zircons, so small, very hard and resistant minerals that were recycled but actually survived this process and that we can now find in new rocks. But for most of them, all this information is lost.
So, and now we've established that there is a lot going on Earth, which is standing in the way of having a perfect record. It's not a perfect book, as we've said before. It's patchy, it's been painted on, and then it's been thrown into the next puddle. It's patchy, it's messy. And
maybe to add here is, for example, the oceanic plates, which are the oldest plate or the oldest ocean crust is 180 million years.
Exactly.
There's no older crust we have, or oceanic crust we have, because they were all subducted at one point.
And that's even additional to lost information or transformed information. Oceanic crust is way more sensitive to recycling than continental crust. So we have to think of oceanic and continental crust as two completely different cases, because continental crust has a lower density. Thomas, do you know the number? We had to learn it.
Something about 2.98 or something like that.
I think that was oceanic. I think continental should be about 2.7 grams.
Oh, I thought you asked me about oceanic.
Yeah, no, exactly. Okay. So terrestrial continental crust has a density of about 2.7 grams per cubic centimeter, while oceanic crust has, as Thomas has already said, a density of about 2.95 grams per cubic centimeter. So it's denser, quote unquote heavier, which is why it's when crust blocks, when crust blocks collide, or plates. Plates was the word I was missing. When plates collide, the oceanic plates are just the ones more likely to be drawn down back into Earth, be subducted because they are, quote unquote, heavier.
Yeah. The picture that is often painted is that the continental crust is swimming on top of the mantle. And this may help to understand the differences in the density. But this is also not completely correct, because the mantle or the upper mantle that we're talking about is not completely molten. Or the asthenosphere. Sorry, there's the asthenosphere between crust and mantle. It is not completely molten. It's actually not molten at all. These are rocks at very high temperatures and very high pressures. And with that combination, rocks can move in a solid way. These rocks are solid, but still can move. You can think, for example, glaciers. Glaciers are solid. The ice is solid, but glaciers are still moving. Kind of like in that way.
Swishing around.
Yeah, swishing.
Very, very slowly.
Yeah.
It's a very diverse topic. On the one hand, we have oceanic crust, which is at max about 180 million years old, while the oldest continental crust is about 3.8 billion years old. And yeah, this might illustrate how difficult it can be to compare different parts of Earth.
Yeah, in the first episode, we just threw in a number of the oldest material of Earth. And I said that the circumhulls zircons are about 4.375 billion years old. And I've researched that again, and it seems like that even that number is still discussed, and that some people are not quite happy with that and say that they're actually a little bit younger. But it generally, like the oldest material of Earth that we have, can be about 4 billion years old, but these are not rocks. These are just, minerals like zircons.
Yeah, and that's the thing. We might have these minerals, certain, very hard minerals, which survive these recycling events, but it's very rare. So, once you have volcanic rock, magmatic rock, I keep saying volcanic, but in general, magmatic rocks, once they have been weathered, eroded, redeposited, sometimes you can make inferences when you look at sedimentary rocks, which magmatic rocks might have been the source rocks for the sediment via certain mineral associations, for example. When you look at sedimentary rocks, you can try to figure out how long this sediment has been transported, because the longer a sediment has been subject to erosion, to transport, the more sensitive minerals are going to be lost.
Yeah, and with that, information is lost, but also new information can be gathered.
Exactly. For instance, you can figure out under which kinds of environmental factors has the sediment been deposited. One example would be that you can have cross-bedding, which results from, ripples. So when you think of ripples at the beach, these structures can be seen in rocks, so that you can make inferences about the exact environment.
Yeah, it's funny to think about, because at some field trips that we were on, we looked at these cross sections of these rocks, and like casually standing there and discussing the orientation of the water movement that happened like 100 million years ago. Just casually, oh yeah, I think the water was coming from the east.
Yeah, and that's pretty amazing, because honestly, it's not that rare that you have sedimentary structures indicating a direction the sediment came from, or some kind of indicator, at least, whether there was water movement, from where the water, from where did the current come, aspects like that. So sedimentary rocks, they are pretty dynamic in that regard, because pretty often they tend to show you a lot about the environment and the conditions in this environment.
Yeah, most of the information, or a lot of information about the original rocks were destroyed, but therefore we get a lot of information about dynamic processes that sedimented them in the first place.
And then we face this problem of metamorphosis, where, I mean, you're more into petrology and mineralogy than I am. I mean, me as a paleontology student, first and foremost, I would say that most information is lost during metamorphosis.
Yeah.
At least about the parent rock, the initial
There's
rock.
a lot of information lost, and what I can comment at is, so I actually don't learn like most of the petrology classes, but I did take all the geochronology classes. All this onology words are difficult. So geochronology is the science of studying the age of, well, different rocks or minerals. And there are ways, and this is something that I really want to discuss in future podcasts. I don't want to go into detail here how this exactly works. But we can look at isotopes within minerals to date the origin of them, the origin of the minerals itself.
So with isotopes being atoms which have, they are the same element. Different isotopes are the same element, but they have different numbers of neutrons in their core. So they're basically heavier and lighter.
Yeah, exactly. And, some of them are stable and some of them are unstable, which is radioactivity. And with that process, we can look back in time. You basically just ask the question, okay, all this element is radioactive and it should have been destroyed. So let's see how much had been destroyed and therefore, well, what time span there was, if this is understandable.
You can try to figure out how long it's been since the metamorphosis.
Yeah, exactly. It's the point. If there is like high enough metamorphosis so that like the chemistry of the rock changes, and if you now date the mineral, you get the age of the metamorphosis, but you don't get the age of the original rock formation. This age was destroyed.
Yeah.
So there's information lost, but we get like new information because we can now see when the metamorphism happened.
Yeah. So we've been talking about how information gets lost in general, but one thing I would like to touch on is that there is a certain bias to which information is lost in geology, because rocks aren't necessarily eroding, eroding the same way. There are rocks which are way more resistant than others. There are some which basically just brittle away voluntarily. For instance, if you have a granite is universally known to be hard, to be resistant. A granite is going to be there for a long time, even if it's been exposed at the surface for tens of millions of years likely. While on the other hand, something like, clayey rocks will break apart physically very, very readily.
The problem is the farther we go in time, like the more information we lose about the very first days or the first moments of Earth, because all these things get recycled and recycled and recycled and recycled again, and we end up with a lot of information about the last millions of years, but then it tends to get less and less and less.
Yeah, it's just a mathematical likelihood, because the younger something is, the less likely it is that it has faced something destroying it.
Yeah.
It's just resisting punch after punch after punch, and it's only very, very few kinds of rocks, or minerals for that matter, will resist the continuous punching.
Yeah.
So,
but would it matter for you if I would now just smoothly move to planetology, or is there something that you want to add at this like first part?
no, I think that's basically what we tried, what we wanted to try and convey. So, yeah, we can
so because
swiftly move on.
first of all, planetology is a beautiful topic. But
yeah, it's okay.
there's, I mean, we now said that we like lose a lot of information about the old times of Earth. But then we can look at other archives to get some information about how the early Earth was like. And therefore, I just want you to look out of the window up in the sky. And if you can't see the moon,
I can.
You probably won't now, I guess. At least for me. But if we look at the moon, we see there's quite some difference between the surface of the moon and the surface of Earth. So on Earth, there are impact craters on Earth. And actually, it's quite interesting. I kind of like impact craters. And I actually was born very close to a large impact crater in Germany, which is called the Nördlinger Ries. But like most of the impact craters we have on Earth are kind of indistinctive and difficult to spot, and for a very long time we didn't even know that they exist. And then now, like with new data and satellite images, we kind of see more and more of these structures. I actually, maybe one thing I can add here. So did you see like videos of the new flight simulator?
Yeah, I did.
Yeah, like the very beautiful graphic and like the, for most of the parts, realistic shape of Earth. So I've actually gone through like a Wikipedia list of large impact craters. And there were a lot that I didn't know of. And then I visited them by plane and just flew over them to see if I can spot them.
And how much success did you have?
Actually, quite a lot. I really think that I learned a lot. I really learned a lot because first of all, there are a lot of large structures I did just not know of before. Kilometers sized. And they're also, I mean, they're not that visible, but once you know it, you kind of like, oh yeah, I see what they mean.
Yeah, but one thing you should have seen is they aren't really as frequent as they are on the moon, are they?
Yeah. And the moon is littered with impact craters.
And why is that?
Well, there are many reasons for that. So first of all, the moon does not have this, well, at least for a very long part of its history, it does not have the rock cycle we've talked about now. The moon's rocks are very old. So on the moon, we have ages of rocks that are younger than 4.4 or 4.5 billion years. And for most of the part, the moon is older than, like the rocks of the surface are older than 3 billion years or 2 billion years. So that's the first point. Like there wasn't like that much recycling that we have on Earth. This is the first part. So the second part is that there is no atmosphere. There is no weathering. There is no rain. There is no wind. All these processes and, well, nature. So plants, for example, and soil producing with that is like a large factor for weathering on the surface. All these processes do not exist. And also because the moon has no atmosphere, generally every asteroid that is pointing to moon will also reach the surface because there's just no atmosphere to stop it. But what we can learn from that is following. If the moon has so many impacts, and not only the moon, also Mercury and Mars to some degree, and many different bodies in our solar system, it would be unrealistic to think that Earth wouldn't have experienced it. Why shouldn't Earth didn't experience it. So with the impact history of the moon and with like the ages of these very large impact basins on the moon, we can also think a lot about how early Earth looked like. And this is, for example, something you can throw in, the late heavy bombardment, which is a period of time in the history of the solar system or like terrestrial planets when a ton of material reached these planets and like reshaped their surface and actually part of their chemistries as well. Again, this is something that we were taught on and on and on in our field. But yet again, it's a point where there's actually still a lot of discussion, and some people claim that things happened a little bit differently. But what we can know is that we look at moon and we see a lot of impacts that are very old. And these are also probably impacts that Earth had at one point in its history.
Yeah, so what we see is we do have a rock record on, of course, our rocky bodies in the universe. It's just that the processes working on these different systems are very diverse, very different.
Yeah.
It works differently on the moon. The moon is less active than Earth.
Yeah.
There are different factors which are important for, reworking on the moon, if you will. Reworking is maybe a too active term for that, but
no, I mean, I guess you can say it.
Yeah, but I mean, it's just. I think what I want to stress here is everything works way slower on the moon.
But with that help, we can get a lot of information about ages of surface structures on the moon. So, as you said, there are actually processes on the moon that erode surface structures. And so, first of all, the surface of the moon, this is layered with a dust layer, or kind of like dust layer, which is called regolith. This is like fine-grained material that was, how would you say that?
It's formed by the impacts, basically, isn't it?
Yeah, formed by impacts and then solar storms, so...
Yeah, so radiation, essentially, it breaks down the rock, bit by bit.
Yeah. And so this is very fine layered materials, and this covers basically the surface of the moon. And this material moves very slowly, but it moves. So first of all, we have the solar wind that actually lets this material move. Then the moon is still moving in some way. So we have like processes in the moon's crust, or like large impacts that led to moonquakes that also led to movement of this surface structure. We have micrometeorites that change the surface of the moon, on and on and on. And, mass wasting in general due to gravity, so material getting pushed down by gravity also leads to some kind of erosion.
Or rather pulled.
Yeah, pulled. Correct. So with that, the moon is still reshaping, but on a very slow process. But with that, we can get some information out of it. And so first of all, we generally say that craters that are smaller than 50 or 100 meters are Copernican ages. So Copernican is the latest timescale of the moon, or the youngest timescale of the moon, and it's basically from now to 800 million years ago. Which in the case of the moon is recent, I guess. 800 million years ago is happened yesterday. So when we see craters that are smaller than 50, 100 meters, we can generally say that they're younger than 800 million years. And this allows us to give some information about, to get some information about the age of specific surface structures. And this is actually something that I've used too in my bachelor thesis. So I also won't go into detail here and tell about it in a later podcast. But it's like a first way to get some information about the nature of surface structures. And actually can go into more detail. Because we have theories or ideas about this erosional rate. Which is called the infill rate. So try to imagine like a small crater or something like that, a small crater, or a small graben, so a small graben structure. Regolith will fill this structure over time. And we actually know, or we think to know, this rate of refilling. And this is something like 5 plus minus 3 centimeters per million years.
So which is pretty rapidly.
Yeah, it's not a lot of movement. But the interesting thing is here, if you, for example, have a graben with a depth of like 1 meter, and it's like fresh looking and crisp looking or something like that, and it has like a depth of 1 meter, then we can say, well, if this is like refilling in 5 plus minus 3 centimeters per million years, and this graben is still visible, then it's probably younger than 50 million years. So it have to formed like 12.5 to 50 million years ago. So this kind of actually gives us a possibility to date small structures on the moon.
Yeah, that's pretty interesting and pretty ironic, I think, that here on Earth, all these kinds of erosional reworking processes are condemned by geologists for destroying our evidence, and up there it creates evidence for you guys. So it's I think it's pretty nice that we can use reworking processes up there. It's pretty nice to see that, or how different things work on different celestial bodies.
Yeah, I guess I will add actually one more thing. This is also something maybe for a later podcast, and I keep saying that, Jesus. But there's something called crater counting.
This is just a little footnote. This is he's been explaining that to me for about 1.5 years now, I guess.
Yeah.
So it's a topic very close to your heart, I guess.
No, it's a conflicting topic.
Love-hate relationship.
Yeah, it's like very useful, but it's like, at least for me, I don't like doing it or working on it. So the idea behind it is very easy. You just look at a surface, or let's make an easy comparison. You have like one surface that is littered with craters of all sizes. The whole surface is littered with craters. And then you have a different surface next to it. And this surface on this area has a lot less craters. The abundance of craters is less. So they're only very small craters and just less in general. So the basic idea is, well, this surface or this area with less craters is probably younger, because at some point the surface had to experience something that destroyed all the craters. This is like just the basic idea behind it. Because over all the time, asteroids will reach the moon and crash into it and create more and more and more craters. And if a surface has less craters, then it probably hasn't experienced that much time on the surface. This is like the basic idea. And then at some point, some really smart people said, well, we can actually use a mathematical function to now not only so that it's now not only possible to relatively date these structures or these surfaces, but to directly, precisely, on the moon scale, date the surface areas. So basically, you just ask the question, how old must the surface been, or how old has the surface to be, that there's this abundance of craters? And this may sound kind of like, not very precise. But actually for the moon, this is very precise. I mean, like, precise on a moon scale, which means you'll be able to say this is like 1.2 plus minus 200 or 500 million years.
Yeah,
I mean, you can get preciser than that. But still, on a moon scale, this is really precise.
Yeah. Yeah, and things like that wouldn't work on Earth. Earth is way too dynamic for that.
This wouldn't work. This is, some people use this for Mars. And already at Mars, it's really difficult to do.
Yeah, but speaking of, could you tell us something about other planets? Because I know you love the moon, but there are more terrestrial worlds out there.
Yeah, so first of all, we have Mercury, which basically is very similar to our moon in that regard. At least in that regard. So heavily cratered. It probably, I guess, experience more influence from the sun because it's just closer. But it's very similar to the moon. The next on the list would be Venus, and Venus is extreme, is probably the right way to put it in many ways. Why I say extreme is especially when we look at the surface of Venus, because the age of Venus' surface seems to be in general younger than 1 billion years.
And why would you know that?
Yeah, so we have some satellites that, visited Venus at some point. For example, Venus Express from the European Space Agency. Or MacLeod. MacLeod, yeah, from NASA. The first problem we have with Venus is that, there are clouds everywhere you look at. So you can't see the surface of Venus. But luckily we have radar. And with the help of radar we can, at least try to model the surface of Venus. And if we look at large impact structures on the surface of Venus, we see that these are generally relatively small, for example, compared to the moon. And also, there are not many of them. They are less abundant. And now with the same mythology like on moon, which I call it now crater counting, we can give some idea about the age of the surface, because now we can look at all the other different planetary surfaces and have an idea how many craters there should be in that size. And with that, we can say that the surface of Venus is probably younger in general than 1 billion years. But it's not very precise, and there are large errors, and we don't know if the surface is the same age at everywhere. We know that there are age differences, but on how large the scale of age differences are, we don't know that yet.
But then again, what's so special about this age of 1 billion years is that our solar system is about 4.5 billion years old. So, it's pretty young.
Yeah, it's kind of mind-boggling because we have no clue why. So there are some theories out there. So first of all, there are catastrophical events that we discuss. unbelievable large volcanism that happened like 1 billion years ago. Like large parts of the mantle actually could have melted and could create this young surface. Some people actually talk about like a mantle, a completely overturn of the mantle itself. Then also some argue that it could be a more gradual process, like just a lot of volcanism happened.
Yeah, I mean, it's the more we look around, the more in general in nature it seems to be that the answer tends to be something more gradual, more complex, less apocalyptic and spectacular. So
yeah, but actually, interestingly, in the case of Venus, as far as I'm on like the newest information, that actually the most of the scientists tend to say that it seems to be like more of a catastrophic event.
Oh, that's interesting, but yeah, I mean, anyway, anything existing before this event may it be gradual or catastrophic and sudden, it's destroyed.
And that's it.
That's the point. That's one case where it would be pretty difficult to determine what happened before. I mean, Venus has a very hostile atmosphere. I mean, yeah, currently it's in discussion to maybe harbor life because of the whole phosphine debate.
Did you see that there were now some newer papers that claim
that there isn't phosphine, I think, or
there's some papers say that it could be like just the noise.
Yeah. I mean, I don't know anything about that. It's just not a field I'm active in, but I mean, they seemed pretty thorough. It seemed like a very multidisciplinary approach, but I just don't know.
Yeah, we don't know
enough about But
we have to work on this.
But anyway, it's the atmosphere is very hostile. It's difficult to work with Venus. Now. Yeah, at least now we don't know what's been before, but yeah, that's pretty interesting. And this extreme atmosphere, then again, I would think that it stresses the surface a lot.
Yeah. So, Venus is a very hostile place.
Yeah. But let's move on. The planetary chain.
I want to throw in here one more thought, because this is like a thought experiment. I just really like it of Venus.
Oh dear, so you know 5 minutes.
I'm doing my best. So you know the Goldilocks zone.
Yeah.
Do you? Yeah. Which tells you at what distance from the sun and what region or area the distance from the sun or of any star is liquid water possible at the surface of a planetary body. Now Venus is too close to the sun to have liquid water on the surface. Yeah. But the sun's intensity actually increases over time. So the Goldilocks zone is not locked, it moves. And it moves farther away from the sun, because the sun's intensity increases. And by that, at some very optimistic approaches, Venus is like at the edge of the Goldilocks zone. Like with the right atmosphere and everything, maybe, could be, yeah. But if you think that the Goldilocks zone was back in time closer to the sun, and this is something like that's not heavily discussed or anything, because it's difficult to do. But at least there is the chance that Venus was closer to the Goldilocks zone than now. With that in mind, and with knowing that we just can't know what Venus looked like, 2 billion years ago, we can't, or 1 billion years ago, we can't know that.
Then again, who knows what will be possible one day in terms of research and in terms of figuring out whether yeah, the rock record there is truly inconclusive, but because you've mentioned before, we don't even know whether the whole surface has been remolten.
Yeah.
Yeah.
But at least there's this chance that Venus may have been more Earth-like than we ever thought at one point in the history. I mean, it has a similar size, and yeah, who knows?
It's trying to figure out about the past of a planet via physics, basically. Or physics and chemistry, trying to figure out, all right, how luminous would the sun have been back then, trying to reconstruct whether, the Goldilocks zone would have been within reach of Venus. It's a good example how to overcome knowledge which is difficult to obtain. I mean, it's modeling, but it's the best attempt, I would say.
Yeah. Venus is hopefully an object for further research in the future. So NASA's thinking of a new Venus mission, and, well, maybe, we don't know. Also, Baby Colombo, so the European Space Agency's spacecraft that is currently flying to Mercury, and will still need some years to do this. It will actually fly by Venus. It actually did fly by Venus now 2 weeks ago. 1 week, 2 weeks ago? Ugh.
I think it should be closer to 2 weeks.
I actually got the images on email from the flyby because of our planetary institute at the university. We have an instrument actually on Baby Colombo, which is called MERTIS. It's like a spectrometer, so to get information about the chemical. Yeah, it's like the chemical, to detect the chemical compounds, the mineralogy of the surface of Mercury. That's like the idea at the end. So, because this is from our institute, this technic thing, MERTIS, instrument. This technic thing, this instrument, we get like a lot of information.
Yeah.
So we saw the builder back then, the images back then.
The build. Oh yeah, here we have a German word of the day: Bilder. Images.
That's boring word. Images and Bilder.
It's a boring word, but what are you gonna do?
Yeah.
So Thomas, back on track.
Anyway,
next planet, please.
Wait, one more thing. So at the flyby, we hopefully can even get some information about Venus. That's all I wanted to say. That took a long time. Next planet.
The Earth, boring. Next
planet, Mars. As far as I'm concerned. So Mars is interesting because at Mars I actually worked. I not worked directly on Mars, but like on a topic. During my internship at the German Aerospace Agency this summer. And this was actually a project that is kind of part of, our topic today. Now, because this is still like an ongoing work, be careful, I guess, about what I'm saying about that. But
have you already published the abstract?
No. I think it's because it's part like of a larger project, and I guess I want to wait.
So spoiler, I guess.
Whoa. Cut it out. No. So Mars is interesting because at one point Mars is really ancient, and it's heavily cratered, and we see, for example, the southern hemisphere of Mars. So Mars is a dichotomy, which means that the northern plains, the northern surface of Mars, it's much lower in elevation than the south. And it also looks a lot different. And the southern hemisphere is like heavily cratered. And with that, we can get an information about like the crustal age of southern Mars. And it is very ancient, so it's older than 3 billion years. Should be.
And then we still within reasonable range in terms of age, I would say.
Yeah. And then the northern hemisphere, it's not that there's not this greater abundance. It has a smaller greater abundance, and it also looks different. It's more smooth, and it appears kind of darker, like on imagery. So with that, we know that, well, the northern lowlands at some point had to experience a resurfacing event. So at some point, these northern lowlands were modified. And the interesting thing about Mars is it's so different than Earth, but on the same time, it's kind of similar. We have wind. We, back in time, had water at some point. I mean, how abundant that water was is still discussed. Could have been an ocean, but it could have also been very periodically, just smaller amounts. We don't know yet. There's ice on Mars, glaciers. So at some point, Mars is kind of similar processes on Earth, but like on a completely different scale. We talk like about wind erosion that happened over millions of years at the exact same spot or exact same surface. So it kind of is very similar, but also really different to Earth.
Yeah, maybe it's, I don't know, I imagine it somewhere in between processes on the moon and on Earth.
Yeah.
Somewhere in between, it's, the sun has a way more intense influence on Mars than on Earth.
3.5 billion is the lowlands.
From that series now. Yeah, I mean it's younger than Earth, but I don't really know whether that has to mean much. But
so we know that some process changed the northern lowlands, and there's a lot of discussion. So first of all, we have volcanic activity on the moon, on Mars, which could have led to this resurfacing event at some points at least.
It's also interesting that these resurfacing events keep coming up, keep being suggested.
Yeah, I mean, in planetary sciences, resurfacing event does not imply the scale. So if you, for example, have a very small surface and like some meters away, an 100-meter sized crater or 100-meter sized asteroid crashes into the moon, and like the surface next to it gets changed, then it's also a resurfacing event.
Yeah, all right. Yeah.
Yeah. Okay, or it's just mass wasting is also kind of like a resurfacing event.
It's mass wasting. Great word.
Yeah. Yeah, so it just implies that the surface was kind of modified at some point.
Yeah.
Yeah, and at Mars for the Northlands, there's also discussion that, and you also have the pictures of like the CGI images of like a large ocean in the northern lowlands that covered Mars.
Yeah, and that's interesting as well, because we do actually seem to have sedimentary rocks there showing, as we've talked before about sedimentary structures implying water movement, and these seem to be present on Mars as well.
Yes, but there are some problems with that. So first of all, as I said before, we talk about different timescales. So who knows what wind erosion is possible to do over billions or millions of years. Maybe in the end it can look like kind of similar to sediments that were deposited like aquatic on Earth.
Yeah.
Okay. And then a good example for that is the new Mars rover of ESA, of the European Space Agency, the Rosalind Franklin rover. There are hydrous minerals at like this boundary from northern lowlands to southern highlands. And we know that these minerals at some point had to have experienced some connection to water. So, like, immediately some people were like, yeah, okay, it was the ocean. It had to be the ocean. But then again, imagine like these sediments being in depth of some 100 meters, even kilometers, with just groundwater or hydrothermal waters. And this could result in like the same thing. But then again,
didn't know that.
Something had to bring them back up to the surface. So what event was that?
Yeah.
You see, it's... I worked on stratigraphy on Mars, and the first thing I meant like, oh, it's probably easier than Earth. Not easier than Earth. No, easier than Earth, but like difficulter than the Moon. But it's complicated. It at some point I was just sitting there and trying to understand what I was seeing, and I just wasn't able to do it.
Yeah, Mars is more complex than we give it credit for.
Yeah.
I mean, this is, I think, speaking for all kinds of terrestrial worlds out there, including the Moon. But yeah, it just goes to show that, yeah, Earth is very complicated, but so are other worlds as well. Yeah. Just on different scales and in different ways.
Maybe to add one more thing to Mars very quickly, because it just fits very nicely to the topic. So the northern lowlands, as we said, have less craters and everything. So the question is, why are these lower in elevation in the southern area? Why? Why is this the case? And then we have the problem. We want to see what's beneath, but all this stuff, that's just all the sediments and volcanic stuff that lays on top the northern lowlands, just doesn't allow us to, well, look deeper into Mars. But what we can do is we can look at the gravity of Mars. And we have some satellites that measured the gravity of Mars at a very detailed scale. And with that, we actually are able to see some of the stuff beneath this material. And what we see from that, and this is interesting, because there are a lot of theories why this northern lowlands could be different or lower or younger. And some say maybe this was beginning plate tectonics. Some say maybe this was like a gigantic bloom of magma that lay beneath this area. Some say maybe it was a large impact basin. There are different ideas. But what we can say from the gravity data is that whatever lies beneath this lowlands is heavily cratered. And actually, it seems like to be the same, or at least near the same age of the lowland, of the highlands. Just because we see so many and so large craters in the gravity data beneath. There are some people saying that it's still younger, but this is still discussed because it's like very uncertain. You can be very precise here. So again, we have some methods to get more information, to look deeper, but it's limited.
Yeah, but once again, concluding, it's a remedy. It's a remedy for something which is very, very difficult to study. I mean, yeah, because we aren't there, of course, but yeah, we don't really know what's going on there. We don't know what's missing. We don't know what has been destroyed in the process, but it's a remedy to try and figure that out.
Yeah. Maybe one thing to add.
As always.
One more thing.
Yeah.
I'm doing the Apple thing. Just for the listeners, there's 2 websites I just want to address here. The first of all would be QuickMap. So just type in LROC, so LROC, quick map. Then you have a map of the moon. And there are a lot of different data or layers that you can add. You can add gravity and all that stuff and chemistry, but I guess it's maybe a little bit too much. But the interesting thing is you can just zoom into every spot you want and you get the highest resolution that we currently have. So for most of the spots, 0.5 meters per pixel. Just addressing this here. Just open, if you have time, open it, go into detail with the moon. It may look kind of boring from far, it's very similar everywhere. But going into detail at some spots, and you will always find something very interesting. So this is for moon, and for Mars, there are many for Mars. So first of all, you can just use Google Earth. So if you download Google Earth, there you can switch to Mars, and you also can actually choose different spacecraft data, and I actually used it while working at the DLR. It's, as far as I know, it doesn't get any updates, and it's limited, but it's easy to get a first view of something. And then if you want to go into more detail, I want to address muted. So muted as not being able to say something. MUTED. Just type in muted Mars. And this is a website that was actually done from one of our people at our institute. It's very easy to handle. And you can again look at different data, and for that I just say look at the high-rise data, and you can get Mars in a detail of up to, I guess, 0.25, so 25 centimeters per pixel, and you can get really close to Mars, and it's stunning. It really is. There's so much to discover. Yeah, I just want to add that here, if we're talking about the surfaces of these planets.
So Thomas, I've just looked at the clock, and I think we're already running about 1.5 hours, so maybe we should move our next section onto the next podcast.
Yeah, I think that's a good idea. I know that there are some things that you wanted to talk about, and I guess this would not fit in within the next hour.
Yeah, exactly. Because what was planned was that I would discuss a little bit about preservation in paleontology and why the paleontological record is even something very different from the usual rock record, why there are certain additional biases in place in paleontology. And I think we'll just move this to the next podcast then. Maybe we could also extend our planned discussion about this whole subject of preservation and the rock record onto the next one.
Yeah, I guess that's the best way. I just got a bit carried away with my planetary science part.
Yeah, and so will I with paleo. So might be the best step. But I think this could be a good opportunity, because we could maybe then extend this discussion about remedies, about how to work with an incomplete record the next time. Yeah. But drawing conclusions for this episode, maybe. What would you say? What would be the key message of your part?
So first we looked at why this record is actually incomplete. We looked at different processes that led to this record that we have today. I've then just kind of moved on to different planets. and showed you that different planets have different records and different processors that work on these planets. So we know that all these planets work different from each other. And I guess what we learn from that is to be always careful when doing conclusions, to always trying to figure out why this or how this record could have been altered before. And I guess it's also important to know that if the answer may be not possible on your record, like for example, looking at the impact history in Earth, we can go to other reservoirs, to other archives, and look there to see maybe if this archive or if this record has different or other other possibilities than our record, for example, here on Earth. So I guess this would be kind of my conclusion.
Yeah.
And
yeah, you need to look at different sources of information to get the full picture, and
yeah,
you have to look at different things to try and figure out how exactly planets as a whole work.
Yeah. Exactly. And I guess this is something that we want to discuss in the next episode, but maybe to kind of tease it, while our record is incomplete and patchy, there are always, maybe not always, but there are a lot of ways to overcome this. We just have to look at other places, for example, to get there. But there are ways that we still can make predictions about the history of our planet or the history about my solar system. Sorry, this was my phone. But we can still make these. We can still think about these. We just have to look at different archives, for example.
Yeah. And maybe before ending this episode, some information on the podcast as a whole, because we have decided that we're going to try and upload episodes all 2 weeks. This is the planned schedule for the future. So part 2 of this discussion is going to be up.
I mean, there are
very
variations to the schedule because we're both studying in the moment. We both have personal lives and we do this podcast for fun. Yeah.
Do we? Do we have social lives, personal lives?
I mean, yeah, kind of. Not in the moment because of Corona.
Kind of.
Yeah.
There's a lot of time for yourself.
But for example, now I wrote my bachelor thesis. I just wasn't able to do the podcast the last week. So that's why the second episode is a bit late. But for now on, we will just try to do 2 weeks. I guess there will come times when also this schedule we are just not able to do the schedule. I mean, at least when you're writing your bachelor thesis, or if we have exams, for example. But yeah, this 2 week schedule is now our plan to go on for the future.
Yeah, I mean, writing a bachelor thesis is the priority, of course. It's there's no way that the podcast can interfere with, important courses, with important exams. Because I mean, we're doing this as an output, essentially, as a means of getting into SciComm, and therefore we don't want this to interfere with our studies.
Yeah, so
but it's fun, and
definitely.
so I'm looking forward doing these episodes.
I'm happy for the next episode because I'm really looking forward what you have to tell me. It just gave me some of the main topics, but I don't know exactly what I will learn the next time.
I think it's gonna be fun. I'm even going to get out of my own comfort zone, and I'm going to talk about plankton for some time next time. So
they have no backbone.
Let's see how this goes. Yeah, they have no backbone, but yeah, they're kind of important. Yeah. So, well, final words.
Well, I really enjoyed this podcast. I had a lot to tell, and there's still a lot more that I want to tell. I couldn't go into detail of many things, but this is a perfect opportunity to go into detail with them in the future. So yeah, I really enjoyed it. I hope you enjoyed it too. I hope you learned something.
Oh yeah, absolutely. I mean, I did, and that's the fun part about this. That's really one of the most fun parts about this, because we can learn from one another, learn about subjects. I mean, I'm really interested into planetology as well, and yeah, through you, I get to learn things I just wouldn't stumble across if it weren't for this podcast, I
guess that's for me the same.
Yeah. So, with that, thank you guys for listening, and
bye.
See you then.
Thanks for listening to the RockyTerrain Podcast. If you enjoyed listening to us, please consider subscribing on your favorite podcast platform. Everything addressed in this podcast reflects our own opinion. You can contact us at 4.5gainthemaking@gmail.com. That is 4.5gainthemaking@gmail.com. All music used is from Kevin MacLeod and was downloaded from filmmusic.io under the Creative Commons license. That is heavy interlude for intro and outro, and home bass groove for intermission. Meanwhile, I think we will go now into in 2 weeks. Well, we will now go into our what is it called? Rhythmus on English. Jesus, heute klappt ja gut. Wollen wir das nochmal mit den 2 Wochen einfach neu aufnehmen? Sorry, das ist einfacher zum Schneiden.
Sketch. Ja.
Oh Mann.
Du hast auf jeden Fall wieder irgendwas, was du hinten dranhängen kannst als Outtake. Jetzt hat mir das Wort Outtake fast gefehlt. Ich wollte Output sagen. Okay. Pause.